In this video, we're going to do a brief introduction to implicit differentiation. Now, so far, we've only differentiated functions where y is explicitly defined as a function of x. So what does that mean? Here's an example of y being explicitly defined as a function of x. Here we have y equals sine of 2x plus 3x. And up until this point, every equation that we've differentiated has looked like this, where y is strictly defined using x's. But that's not always the case. And if we want to differentiate a function where y is not explicitly defined using x's, we have to use implicit differentiation. Take this equation, for example. Here we have sine of xy equals x squared plus y. This is an equation where x's and y's are commingled together. And in this situation, it's impossible to solve for y on one side of the equation and x's on the other side. In other words, we can't solve this equation for y so that y is explicitly written using x's. It's just not possible. So can we differentiate equations that look like this, where we can't solve for y? The answer is yes. And the way that we do that is by using the chain rule. So here we're asked to find the derivative of y squared, where y is equal to f of x. Or another way to say that is y is a function of x. So if we want to differentiate y squared, where y is a function of x, that would be the same thing as saying we need to differentiate f of x squared because y is f of x. Notice that we have a function, f of x, that is being functioned, in this case, squared. This is just another way to express or illustrate a composite function, or a function within a function. And if we remember, when we were learning how to differentiate functions within functions or composite functions, we used the chain rule. And we identified our inside function and our outside function. And the derivative was found by multiplying the derivative of the inside function by the derivative of the outside function. Here, our inside function, u, is f of x, because f of x is inside the parentheses. But f of x is equal to y. So our inside function here, u, is y. That means that u prime is the derivative of y with respect to x, or y prime if you want to write it that way. And this makes sense, because in every equation that we've differentiated thus far, whenever we found the derivative of y equals whatever, wherever we saw a y, what did we write? We wrote y prime because that is the derivative, but another way to write y prime is dy over dx. So the same thing holds true here. If we want to differentiate y with respect to x, it's dy over dx, or y prime. Our outside function here we're going to call w, just so there's not so many y's floating around this thing. In our previous videos, when we did examples using the chain rule, we always let the outside function be y. But here we've already got a lot of y's floating around, so I'm going to let the outside function be w in this case. If the inside function, u, is y, then that means the outside function is u squared. And the derivative of w, or w prime, is 2u. And now using the chain rule, we find the derivative by multiplying u prime times w prime. And that gives us 2u times dy over dx. And u is equal to y. So we back substitute y in for u. And that gives us 2y times dy over dx. And that's the derivative of y squared with respect to x. Now let's talk about a way to shortcut this whole process. When we're finding the derivative of an equation that is not explicitly defined as y in terms of x, or y using x's, here's an easy way to do it. Notice that 2y is the derivative of our original expression y squared. So when we find the derivative implicitly, whenever we see a y function, we're just going to take the derivative of that y function the way that we normally would. But then here's the extra step that we have to take. We're always going to add dy over dx to that expression. Now, when I say add that to the expression, I don't mean add dy over dx. We're going to multiply the derivative of the y function by dy over dx.